Assalamualaikum students. Today we start exercise 1.3 limit of a function and theorem on limits. Concept of a limit of a function is the basis on which the structure of calculus rests. Before the definition of the limit of a function, it is essential to have a clear understanding of the meaning of the following phrase. Meaning of the phrase x approaches 0. Suppose a variable x assume in succession a series of values as 1, 1 over 2, 1 over 4, 1 over 8, 1 over 6. As we note that the denominator increasing, and also write as 1, 1 over 2, 1 over 2 square, 1 over 2 cube, 1 over 2 4 up to so on. We notice that x is becoming smaller and smaller as n increases and can be made as small as we please by taking n sufficient large. The unending decrease of x is symbolically written as x tends to 0, because if we increase in denominator it is approaches to 0 and is read as x approaches 0 or x tends to 0. The symbol x tends to 0 is quite different from x equal to 0. X tends to 0 means that x is very close to 0 but not actually 0, and x is equal to 0 means that x is actually 0. Phrase x approaches infinity. Suppose a variable x assume in succession a series of values 1, 10, 100, 1000 and 10,000, also written as 1, 10, 10 square, 10 cube up to 10 raised to power n. It is clear that x becoming larger and larger as n increase and can be made as large as we please by taking n sufficiently large. This unending increase of x is symbolically written as x tends to infinity and is read as x approaches infinity or x tends to infinity. X approaches to a means it is written as x tends to a, which means x is sufficiently close to but different from the number a. Both the left and right side of a become smaller and smaller as we please, but x minus a is not equal to 0 because they are not equal. Concept of limit of a function by finding the area of circumscribed region, regular polygon. Consider a circle of unit radius. Unit radius means its radius is equal to 1, which circumscribes a square four-sided regular polygon. The side of square is square root 2 and its area is 2 square unit. It is clear that area of inscribed four-sided polygon is less than the area of circumcircle. Now bisecting the arc between the vertices of the square we get an inscribed 8-sided polygon as shown in figure 2. Its area is 2 square root 2, which is closer to the area of circumcircle. A further similar bisection of the arc gives an inscribed 16-sided polygon as shown in the figure 3 with area 3.061, which is more closer to the area of circle. It follows that as the number of sides of inscribed polygon increase, the area of polygon increase and become nearer to the 3.142, which is the area of circle of unit radius, because area of circle is equal to pi r square, and now we have radius is equal to 1. It means the area of circle is 3.142, which is the value of pi. We express the situation by saying that the limit value of the area of the inscribed polygon is area of the circle as n approaches infinitely. Area of inscribed polygon is tends to area of circle as n tends to infinity. Thus, area of circle of unit radius is 3.142. Next is numerical approach. Consider the function f of x is equal to x square. The domain of f of x is all the real numbers, because at all real numbers it gives real values. Let us find the limit of f of x cube as x approaches to 2. The table values of f of x for different values of x as x approaches 2 from left and right is as follows. We start from value 1, then 1.2, 1.8, 1.9, and then closer values 1.99, 1.999, and then 1.999, and next from right side 2.001, 2.001, 2.01, and up to 3 we find all the values. The table shows that x gets closer and closer to 2 from both sides, get closer and closer to 8 as we note in the value their range. We say that 8 is the limit of f of x as x approaches to a2. Therefore, limit x tends to 2, x cube is equal to 8. Limit of a function. Let f a function f of x be defined in an open interval near the number a. It is as x approaches a from both left and right side. F of x approaches a specific number L, then L is called the limit of f of x as x approaches a. Limit x tends to a, f of x is equal to L. Read as limit of f of x as x tends to a is L. It is neither desirable nor practicable to find the limit of a function by numerical approach. We must be able to evaluate a limit in some mathematical ways. The theorem on limits will serve this purpose. Their proofs will be discussed in higher classes. Theorem on limit of a function. Let f and g be two functions for which limit of x tends to a, f of x is equal to L, and limit of g of x at x tends to a is m. Then sum of two functions is equal to the sum of their limit. Limit x tends to a, f of x plus g of x is equal to their sum of their limits L plus m. Here we have an example. Limit x tends to 1, x plus 5. We separate limit and then apply the limit and get the answer. And same process for the negative sign. The limit of a difference of two functions is equal to the difference of their limit. If k is any real number, then k f of x limit x tends to a become kl, and we apply the limit in example 3x x tends to 2, it becomes 6. The limit of the product of the function is equal to the product of their limit. And limit x tends to 1, it becomes equal to 10. Limit of quotient of the function is equal to the quotient of their limit, provided the limit of the denominator is non-zero. We have two functions f of x and g of x in fraction form, and their answer is L over m, their limit. As in example, we put the limit in numerator and denominator and get the answer. Limit of f of x whole power n, where n is an integer, and then we take the limit and get the answer as we shown in the example. We conclude from the theorem of limit that limit are evaluated by merely substituting the number that x approaches into the function. Next example, p of x a x raised to power n, and then we reduce the power. It is an polynomial function of degree n. Then show that limit x tends to c, p of x is equal to p of c. Using the theorem on limit, we apply limit x tends to c and we replace x by c, so it becomes polynomial in c. Therefore, the required result is limit x tends to c, p of x is equal to pc. Limit of important functions. If by substituting the number that x approaches into the function we get 0 over 0, then we evaluated the limit as follows. We simplify the given function by using algebraic technique by making factors of if possible and cancel the common factor. The method is explained in the next example. Now here we have a proof. Limit x tends to a x raised to power n minus a raised to power n x minus a n minus 1, where n is an integer and a is positive number greater than 0. Now in case 1, we suppose n is a positive integer. By substituting x tends to a, we get 0 over 0 form, so we make factors as follows. Now factors of numerator x raised to power n minus a raised to power n, the generalized form of a cube minus b cube. In a cube minus b cube we have a minus b, a square plus ab n plus b square, but there we have general form x raised to power n, a raised to power n, it becomes x minus a, x raised to power n minus 1, then its power reduce, n minus 2, n minus then 3. In third term we write x raised to power n minus 3, and at the end x is removed, and a from starting we have a raised to power 0, then a raised to power 1, a raised to power 2, at the end a raised to power n minus 1. Both the power are same from start with x and end at a. We replace this formula in numerator and then x minus a cut each other, Now we have a polynomial function, then we put in place of x is a dot a raised to power n minus 2. We add these powers, all a with power n minus 1. We add these values are in numbers is equal to n. If we write 3 times x and add these values, it becomes 3x, and these values are in number are n, therefore n raised to power n minus 1. In case 2, suppose n is a negative integer where m is a positive integer. Now we replace n by minus m. X raised to power minus m means 1 over x raised to power m, and a raised to power minus m means 1 over a raised to power m. Then we take their LCM and we get this value, and then apply limit. In first bracket we replace x by m, and in second bracket we apply case 1, which is equal to n a n minus 1, because there we have a variable m, number m, it becomes m a m minus 1. Simplify this, both the a in denominator remove from the numerator, it becomes a raised to power minus m and minus 1, because minus m is equal to n, therefore it is equal to n raised n and a raised to power n minus 1. Now in this example, if we substitute x tends to 0, it becomes 0 over 0 form. So rationalize the numerator. In numerator we have a formula a square minus b square, a cut by a and x by x. So it is 1 over square root a plus square root a, and it becomes 1 over 2 square root a. In this example, x square minus 1, x square minus x, if we put the values, it becomes 0 over 0. We rationalize it or factorize the numerator. A square minus b square is equal to a minus b, a plus b, and in denominator we common x, and then cutting x minus 1 by x minus 1, and then we put the value. In second example, we again the numerator we factorize it, like we make it x square root whole square and 3 square root whole square, and it becomes plus and minus, and we got the negative value, and then put the limit to get the answer. Limit at infinity. We have studied the limit of a function where x tends to c. Let us see that what happened to the limit of a function c is positive infinity or negative infinity. Limit x tends to positive infinity, x is not equal to 0. This function has a property that the value f of x can be made as close as we please to 0 when the x is sufficiently large. When the denominator increasing, the value close to the 0. And as the limit extends to minus infinity, this type of limit are handled in the same way as x tends to positive infinity, because both gives the zero answer. The following theorem is useful for evaluating limit at infinity. P be a positive rational number now is defined, then limit extends to infinity and extends to minus infinity gives the same answer, 0. X over 6 over x raised to power 2. We apply limit and it gives 0. And then again we have a function minus 5 over square root x. It also gives 0. In all these cases we have the same answer, equal to 0. If denominator is a variable and approaches to infinity, a method for evaluating the limit at infinity. In the case we first divide each term of both the numerator and the denominator by the highest power of x that appears in denominator and then use the above theorem. In this fraction, example number 2, we have the higher power in denominator is x cube. We divide up and down by x cube all the terms, and then we put the limit x tends to infinity. We apply this method only when we have a fraction and limit x tends to infinity. In example number 3, in the denominator we have the highest power x raised to power 5 and limit is minus infinity, so we divide numerator and denominator by minus x raised to power 5, simplify and put the limit. In example number 4, again fraction and limit extends to infinity, but in the denominator we have highest power x square. In square root it is x square, but when we take its square root it becomes x. Element is negative, so we divide up and down by minus x, and in square root we divide with its square, x square, and in numerator we divide by x. In second case we have limit positive infinity, and in denominator we have highest power x square. In square root it becomes x, and we divide up and down by x, and in square root we divide by x square, and then apply the limit. When we apply the limit, when we have infinity in denominator it becomes 0. Here we have a 2 over x. 2 over infinity is equal to 0, and 3 over x square, 3 over infinity is also equal to 0. Now we have another proof. We use binomial theorem to prove this. 1 plus 1 over n whole power n is equal to e. E is like a pi, a constant value. Now we apply binomial theorem. Binomial theorem is 1 plus x raised to power n is equal to 1 plus nx. N minus 1 2 factorial x square, n minus 1 n minus 2 over 3 factorial, and x cube. We replace x by 1 over n, and in second line we simplify these values, cutting these values, and we get 1 minus 1 over n, 1 minus 1 over n, and 1 minus 2 over n, because in second term n cut by n, and in second term third term n cutting by n square, and 1n is multiplied in the bracket, and in third term n cut by n, each term divided by n, first n cut by n, second factor divided by n, and third factor divided by n, because we have n cube. And when we apply n tends to infinity, 1 over n, 2 over n, 3 over n all tends to 0, because 1 over infinity is 0, 2 over infinity is 0, 3 over infinity is 0, and the remaining values are these. When we simplify and add, it becomes 2.718281, which is the value of E. No deduction. Now in second line we have the proof in last page, and the above is deduction. We notice that the value in the bracket and its reciprocal in the power, then it is equal to E. We replace x by 1 over n and n by 1 over x, and if x tends to 0, then n tends to infinity. Another proof, limit x tends to 0, a raised to power x minus 1 over x is equal to log e base and a. In numerator ax minus 1, we put it equal to y. We move minus 1 to the right side, and then taking log of both sides, it is equal to x is equal to log a1 plus y. Property of log. Now we replace the values. If x tends to 0, y also tends to 0. Now we have the question, ax minus 1 is equal to y and denominator x is equal to log a1 plus y. We move the numerator y to the denominator, it becomes 1 over y, and any value before log, it becomes the power of the base. It is the rule of log, and we apply here the previous theorem, 1 plus y whole power 1 over y is equal to e, and we move this log to the numerator, it change its base and the value, and it becomes log ea. And its deduction, we replace a by e, and in the answer log ea, log e, and we replace a by e. If we have the base and the value are same, it becomes equal to 1. Same is there. Important result, x tends to infinity, e raised to power x is infinity, and limit x tends to infinity a over x is equal to 0. Next we have some examples on this theorem. First is 1 plus 3 over n, and if the power is the denominator of the inner values is equal to e, we make the power is equal to the reciprocal of the inner value 3 over n inside the value, and the power is n over 3. We change in the power, we move 2 to the outside and multiply by 3 and divide by 3, it becomes 6. So therefore the inner value is equal to e, and answer is e raised to power 6. In second example, we have the value 2h, and we make in the power 1 over 2h, we multiply and divide by 2, so it becomes e raised to power 2. Next is sandwich theorem. We have three function f, g, h. Their condition is f is less than g is equal to and less than h, and there are in open interval c, except possible value at c inside the open interval is all the limit or L. Now we apply this rule in the upcoming theorem. Limit theta tends to 0, sine theta over theta is equal to 1. If the angle of the sine and its denominator are equal, then it is always equal to 1. Now we apply the technique. Take theta a positive acute central angle. Acute angle means less than 90 of a circle with radius 1. OAB represent a sector of a circle. We note from the diagram AOB sector of a circle and OAOB radius are equal to 1. In diagram OCB, sine theta is, some people have perpendicular over hypotenuse BC over OB, and OB is equal to 1, therefore BC is equal to sine theta. In triangle OAD, tan theta is perpendicular over base AD over OA, and OA again equal to radius equal to 1. Now in terms of theta, the area are expressed as, we have some construction there. We draw OB to D and AD perpendicular to OA, because AD is tangent to the circle at point A, and draw BC perpendicular on OA, join A to B. Now first we have a triangle OAB triangle. Area of triangle is equal to 1 over 2 height multiplied by base. Its side is BC and base is OA, and BC is equal to sine theta and OA is equal to 1 radius. Area of sector OAB. Area of sector's formula 1 over 2 r square theta. Its side is OA, OB and curved side BA, and radius is 1. Area of triangle OAD, 1 over 2 perpendicular over base. Base is 1 and height is AD, which is equal to tan theta. Now from diagram, greater triangle is OAD, then sector OAB, and then triangle OAB. And smaller triangle is OAB, then sector, and then triangle is OAD. We put these values, their areas, then we divide by 1 over 2 sine theta. We get the result 1 less than theta over sine theta, 1 over cos theta, because tan is sine over cos, and we divide by sine theta, it becomes 1 over cos. Then we reciprocal all these values, inequality sign change, and then we apply limit theta tends to 0. At theta tends to 0, cos 0 is equal to 1. Now because at the right and left side both are equal to 1, therefore by sandwich theorem the middle value sin theta over theta is also equal to 1. Now we apply these rule in example. We have, if the angle and the denominator are same, the limit approaches to 0, it becomes equal to 1. Now we have here 7 theta over theta. If we numerator divide and denominator divide by 7, and sin 7 theta over 7 theta is equal to 1. We let there x is equal to 7 theta and theta is equal to x over 7. We replace these values. Sin x over x is equal to 1 and we left with the value 7. In 1 minus cos theta we rationalize it by 1 plus cos theta. 1 plus cos and 1 minus cos is equal to 1 minus cos square theta. 1 minus cos square theta is equal to sin square theta. And we arrange these values like sin theta over theta, and 1 over 1 plus cos theta. Sin 0 is equal to 0. Sin theta over theta is the theorem, is equal to 1, and at the end 1 plus cos 0. Cos 0 is also equal to 1, and all values are multiplied by 0, therefore it is equal to 0. Okay student, try to understand and solve all the example and for theorem, very important lecture of first chapter. And if you have any problem then send it to me. Jazakallah and Allah Hafiz.